Hello everyone, my name is Braden Moore. I'd like to thank all of you for being here today. Before I go into what my project is about, I'm going to talk a little bit about myself. So for elementary school, I went to Walnut Hills. I did some stuff with Scratch, and that's really what first got me into doing things with coding. For middle school, I went to Challenge School, where I did some more stuff with coding, specifically with doing things with the calculators. And then high school, obviously, Grandview. I've taken all of the programming classes that we have here, the Intro to Programming, Game Design, and the AP Computer Science. I took those freshman year, and since then I have done things with coding since then, with video game design, and now my senior project. So next year I'll be going to Colorado School of Mines, and I plan on double majoring in mechanical engineering and computer science. I also am an engineering intern at Riata Engineering and Machine Works, and I've been a member of Colorado TSA, which is Technology Student Association, for the past 7 years, and a state officer for the past 4 years, which, as a part of that, I've been able to do some things with coding with video game design. So for my project inspiration, originally I was planning on doing something with augmented reality, such as the Microsoft HoloLens. However, a consumer version of that has still not been released, and I was not able to get access to a developer copy, so I couldn't really do anything with that. But I still wanted to do something with image processing, which led me to object recognition. So for my project objectives, my first objective was simply to create software that could take in images and process them, and then store them for later use to be able to recognize objects in it. My second objective was to learn how to use MATLAB, specifically in image processing, because I hadn't really ever used the software before, but I knew it was extremely powerful in doing things with high-level computations, so I wanted to learn how to use the software. And then my next one was to learn basic object recognition algorithms, so being able to take the images that I had processed and actually figure out what objects there are in those. My fourth objective was to be able to develop a system for the user of the software to be able to specifically assign attributes to the objects that are being stored. So like if you had a picture of a blue ball, then the user could say, like this object is blue and this object is spherical, and then be able to have later functionality based around those. And then my last objective was to be able to create a learning component, which for most object recognition algorithms, the programmer basically has to say, this is what the program needs to look for, while what I was planning on doing was having the program actually be able to figure out specifically what it should be looking for the most efficient way to recognize the object. So for my advisory committee, my expert advisors were Mr. Greg Bolendum, the space software architect at Lockheed Martin, and Dr. Richard Charles, the STEM director for the Trader Creek School District. My support advisors were Mr. Jay Moore, my father, and the CTE director for Trader Creek Schools, Mr. Daniel Smith, a history teacher here at Grandview who has had a profound impact on me as a student, Chad Lewis, a friend and classmate, and Jason Cyrus, a friend and engineering undergraduate at CU. So for my job shadow, I went to Lockheed Martin to shadow Mr. Bolendong, and I learned things about the coding behind some satellites such as the Cyrus and the GOES weather satellites. So for my company logo, it's comprised of two parts, arc and light. The arc representing progress, and light and the color gold representing inspiration, and also, not gonna lie, a little bit just because it sounded cool. For my project timeline, in September, that was basically just when I was learning MATLAB and messing around with some different things with taking in images. October, I worked with blob detection and analysis, which is kind of a rudimentary object recognition algorithm that I'll go into a bit more later. November, I originally planned on doing stuff with databases and object profiles to actually be able to store the results of the images that I was analyzing. Instead, I ended up working on the software architecture and functionality, because my original plan was to create the algorithms and then kind of create a program around those and implement them, but I ended up finding it much easier to create the program first and then implement the algorithms into that. So in December, I researched more advanced algorithms that would be better suited to general object recognition. January, I originally planned on implementing those algorithms. I didn't know at the time, so I just simply had the advanced algorithms. I ended up researching shape context and foreground isolation, which I'll get more into that, what that is later, but it has to do with the more advanced algorithms. February was originally, I was planning on comparing the results of the analysis to the stored examples. I ended up implementing foreground isolation, and in March I was planning on having that dedicated to be just refinements and optimizations and making sure everything ran smoothly. I ended up being a little bit behind here and worked on shape context and example comparison and wrapping up the program. And then in April was preparation for the final presentation. So for my project, first off, if I show this water bottle in front of you, you can all immediately tell that this is a water bottle. However, a computer isn't necessarily able to do that as easily, because when we look at the world, we see lines and colors and different lighting that helps us determine what we're looking at by comparing to our memories and previous experiences. But when a computer looks at an image, all it sees is just a series of numbers. And so my software was basically taking those numbers from the image and making meaningful data out of it by detecting what object was in the image. Which this differs from current software because most things that are out there right now are tasked with taking some specific thing that you know what you're looking at, like iris recognition or like quality control in a factory scenario, which would be taking like some example that you know you're looking at and then comparing differences from that, from what you're getting in. While what I'm planning on doing, or what I did, excuse me, I was able to take a variety of different images and compare them to examples to find a variety of different objects. So applications for such software could be generalized object or generalized artificial intelligence, like an Android or something like that, where it could have a camera that would be able to scan the environment and determine what objects it's looking at to get its bearings within the world. So the first steps I took, first off, like I said, was learning MATLAB. Then I also did a little bit with blob analysis, which a blob stands for binary large object, which these light sections right there are blobs extracted from this image right here. This is the output of the one of the first things that I had coded, and it basically just detected where the objects were in the image. Which there are a number of things that you can do with blobs, such as determining the ratio of the width to the height or the area. But the issue with this is that it's not really applicable to general object recognition. It's more towards the quality control side of things, where you know what you're looking at and you can find differences between things. But if you have a variety of different things that you're comparing between, this isn't necessarily able to discriminate between them. So I then did some research into other algorithms such as histograms, and this is an example of a histogram from an image, which is basically just a one-dimensional graph that maps out the brightness values within the image. However, this also wouldn't necessarily work for general object recognition because it doesn't store any spatial data, so you could have two completely different images that would happen to create a similar histogram. And we could look at those images and tell that they are clearly completely different, but the computer wouldn't actually be able to tell them. The next algorithm that I looked at was Fourier transforms, which I'll admit I don't really know that much about this because I was quickly able to determine that it also would not apply to my software, but it basically takes an image like that and breaks it down into component images there, which it's very good for determining differences from that original image. But as with the other algorithms that I mentioned before, if you have a number of different things you're comparing to, it's not able to determine your changes. So what I ended up going with was using edge detection, which basically takes an image such as this and then determines where the sharp gradients are, and then creates a white line along it, as you can see on the right side there. And so in order to quantify that, I use an algorithm called shape context, which basically takes a point on those edges, creates a circular grid such as this, and then maps out where all of the other points are in relation to that point. Another part I also had to do as part of that was foreground extraction, which the reason for that is just because the background could create edges that would throw off the results of the shape context. So how my program works, first it takes the image in and goes through the foreground extraction, which I'll go over more in depth how that works in a minute. Then it runs it through an edge detection algorithm and then shape context that I mentioned before to quantify the data of the positions of all of the edges. It then compares the histograms created from that. In this case, a histogram would be the output of the shape context being the two-dimensional image mapping out where each of the points are in relation to the grid. So this flowchart goes over how the foreground extraction works. First, it takes the input image and then breaks it down into 8x8 pixel blocks with a 4-pixel overlap, and then determines each of these features for it. Light distance and color distance are the brightness and color, respectively, of the 8-pixel block with regards to the average. So if it was a very different brightness or color from the average of the image, it would have a bright value, while if it was similar, it would be a darker value. Contrast and sharpness are just the local contrast and sharpness of the image within that block, where a brighter value would indicate a higher value. And then edge strength is basically just how many edges pass through that block. And then cluster density weighting, I'll get to that in a minute. It's basically how the computer determines which of the feature maps to use. So this shows an example output of my program for extracting the main subject. So you have the main, or the original image right there, and then each of these 5 images here are the different features. And so like edge detection here, or the edge strength, excuse me, and then the contrast and sharpness there are better representations of the main subject, because you can see there's more bright values where the actual butterfly is there, and much less in the background compared to these two, which have much more bright points in the background. So this is where the cluster density weighting that I mentioned before comes into play, where it basically is a way of measuring how many and how close together each of these bright points are. So that's what the number is above each of these. And so a lower value would indicate a higher density. And so it takes the 3 lowest values and then adds them with the lowest value having the highest weight to create this map here, used to create the mask for the main image to extract the main subject there. So once we have that, we can then proceed on to the next part of the algorithm. So as I mentioned before, shape context gives a way of quantifying the locations of each point along the edges of the object. So here, the point on the image is used as a basis, and then the other points are mapped on the circular grid into an image such as these. One issue with this, though, that I had to be careful about was, you can see here these have very similar points on each of the different A's, which create very similar output images. But this one here, even on the same image as that, created a very different output. So one thing I had to do was figure out how to figure out a corresponding point between each of the images. So what I ended up using was the centroid of the image, which is basically the weighted average of the X and Y values, effectively the center of the mass. So this flowchart basically goes over how the edge detection and shape context works. First, it takes in the input image, runs it through an edge detection filter, and then locates the centroid, as I just mentioned, and then it constructs the grid around 95% of the points to account for outliers, and then counts the points in each of the bins in the circular grid. It then normalizes the range to 0 to 1 to account for having different resolutions of images, creating different ranges of in the numbers of points. So this shows the output of two different images of a butterfly and an airplane. And as you can see, it creates two very different histograms. However, if I have two of the same class of object, then the output is much closer together. And so from here, I can then compare the output of the test image to stored examples. And so if I have the first point there and the first point there, I can then figure out the difference between those and then do that for every point and add them together. So in this case, a lower value would indicate a closer match. And one thing, if you have this water bottle, you can tell that it's a water bottle no matter which way it's facing. A computer isn't necessarily able to do that though, without being explicitly told how to do it. So in order to account for rotation, I basically rotated each of these images so that the last row there then got moved to the front and so on for each one to account for a pattern that can be shifted. So once again, these are my project objectives that I had. I was able to create object recognition software in MATLAB that was able to take in objects, process them, and be able to give a usually accurate result off of what the object was. However, I was not able to do anything with the user-defined tags because I ended up underestimating the scope of what I was trying to accomplish, and so most of my time was spent researching the algorithms for object recognition. I was somewhat able to accomplish the learning component because the main subject detection was able to adaptively decide which of the features to use. However, it was still not to the extent that I had originally anticipated. And here are just some screenshots of the final program. This is the main menu here. You can see you can either get an image, which can be from a file, or I also added the ability to do it from a phone camera, and then be able to process it, and then also to add examples to be able to compare it. And then this, once again, is the output from the main subject detection, and then the output from the shape context, and then the final output from the program. And then this shows the matches from those examples that I've been showing. It is generally pretty accurate. The first and the third closest match were correctly identified as a butterfly. Unfortunately, it's not perfect. As you can see, it sometimes thinks butterflies are airplanes, but for the most part, it was accurate. So yeah, then this just shows the ability to add an example where it shows the image and then a preview of the histogram to be stored. Then here's my bibliography. Any questions?
Questions?
So is there any application for this commercially besides like the HoloLens? Like what do you think you could apply this to?
One thing that I thought about is you could have it like at a grocery store where instead of scanning the barcode on each of the objects, like you could just show it in front of some sort of a camera and it would be able to tell what object it is. Then, like I mentioned before, you could also do things with artificial intelligence and being able to get its bearings in the world, or like a drone where you could have a camera attached to that that would be able to navigate based on it.
So you said before for your shape context that you picked the centroid of the image as the point of reference. What if that centroid isn't in the foreground of the image, for example, if you have like a U shape?
Theoretically, it should still be accurate because the grid is constructed to encompass 95% of the points, so it would still be able to account for those points, and then it would only have data along the outer ring of that. And so, if you were comparing it to another object that was the same, it would still you would be able to compare those different outputs. It would still.
So as you used your water bottle as a example, so if you're looking at it straight on, it's kind of a cylinder. It looks like a rectangle with a little bit of tapering at the top. And then if you were looking at the side, it's a circle. And you were to do your centroid and histogram, and then were to rotate the histogram, does it still recognize it as the same object?
In In that case, it wouldn't, because rotating it in that way would cause it to have a different outline. And so rotating it like that just means like if you have this rotate this way or this way, as long as it has the same outline, it will work. But rotating it in that way would cause it to have a different outline, and therefore not.
Why did you use a circular grid as you were doing the analysis of the points versus just rotating it?
Just to avoid distortion in different rotations of the image.
Any other questions? All right, thank you. Good job.